All right, this is the second lecture for chemical equilibrium. If you're following along in the Burge book, this is chapter 15. So today what we're going to talk about is heterogeneous equilibria. We've been talking about homogeneous, but not all reactions are homogeneous or occur in homogeneous conditions. We're going to talk about manipulating the equilibrium expressions and equilibrium expressions only containing gases. I can't stress enough about this chapter. This is the tools chapter, and you have to master chapter 15 to do chapter 16 and 17. So 16 will introduce new terms like pH and POH and acidity constants and basicity constants. That'll be the new material, but chapter 16 expects you to know and have mastered chapter 15, the materials in it. So this is the tools chapter to do equilibrium problems in chapters 16 and 17 that have more direct application to careers in pre-med, pre-pharmacy, pre-nursing, or just as a chemist. So that's what we're going to focus on, these tools. So when you look at, the foundation of all equilibrium problems, let's just kind of review just a little bit from the last exam, the last video, is that you have to have a balanced chemical equation. All right, so you must have a balanced chemical equation. If you don't have that, then it's going to be a near impossible to figure out how to do an equilibrium problem. I'm having a little bit of problems. All right. So here we have it. Here we have carbon dioxide. Notice it's in the gas phase. So you want to write make sure that you write the phases of matter, because it is going to make a difference here. We're going to react carbon dioxide with carbon solid, and that's going to form 2 moles of carbon monoxide gas. So when we go write the equilibrium expression, normally what we would do, we would write the product raised to the coefficient, all right, coefficient, divided by the reactants raised to their coefficients. These happen to both be 1 here, okay? So the carbon, that concentration, remember this is moles per liter, that concentration is not going to change appreciably through the course of the reaction. So let me kind of give you a visual of this. You have a reaction container, and we'll just say it's sealed off here. And you have a pile of carbon here. It's a solid. So this is my carbon, and it's a solid. And then you have carbon dioxide gas up here, and these two things react and they form moles of carbon monoxide gas. So let's say that this much carbon was consumed, but I just darkened there, and so now we only have this much carbon. What is the molar concentration, do you think, of this amount of carbon left over versus the entire pile of carbon? So think about that for a minute. Maybe you want to pause the video, but think about what is the concentration of the carbon left over here versus the entire pile of carbon. Well, the concentration is going to be the same. Moles per liter is an intensive property. That's why it was important to talk about intensive properties in Chem 170, Gen Chem 1. So it doesn't matter whether I have a large pile of it or a small pile, the concentration is going to remain constant. And because it's going to remain constant, we move the concentration of the carbon over to the left-hand side of the equation with the equilibrium constant. So these are now both constants, and we integrate those into the equilibrium constant. So it is important that there's carbon present. If there was no carbon present, this reaction would not happen. So you do have to have, as long as there's some carbon present, this reaction will continue to happen. But the concentration remains constant because it doesn't matter whether I have a large pile or maybe even more of this is consumed. I just have a little bit of carbon left. The concentration remains the same. So notice that how this has simplified the equilibrium expression. Now you have the equilibrium constant at concentration is equal to the carbon monoxide concentration raised to the coefficient, the second power, divided by the reactant carbon dioxide. So this is called a heterogeneous equilibrium because up here you have a gas, here you have a solid, and here you have a gas. And pure solids and pure liquids will not change in concentration appreciably and will be integrated into the final equilibrium constant. Okay, so let's look at the next slide. The next slide we have 4 chemical reactions that reach equilibrium, and we know that they can occur. Equilibrium can occur because they're reversible. You can see that tells you it's a reversible reaction. So what I want you to do is write the equilibrium expressions for all these reactions, keeping in mind that pure solids and pure liquids, their concentration does not change appreciably through the course of the reaction, and therefore they will be integrated into the equilibrium constant. All right, so stop the video. Try to write these out. All right, welcome back. So let's see what you have here. So just let's make some notes here. This is in carbon. Calcium oxide is a solid. And so is calcium carbonate. So those will be integrated into the equilibrium constant. Here's pure liquid. Mercury, that will be integrated in the constant. Notice these are aqueous. That is not pure liquid. Aqueous means dissolved in water, dissolved in water. And so these will be in the expression. These will change appreciably through the course of the reaction. Again, this should not be part of the expression. It should be it's part of the expression. It's just integrated into the equilibrium constant. Let's be technical about it. All right, same thing here. This will be integrated into the equilibrium constant. This will be integrated into the equilibrium constant because it's a pure solid. And then we go down here and look at this last one, and again, this will be integrated into the equilibrium constant. So identify those, and then the next thing you want to do is to start writing the expressions. And so here's your solutions, and hopefully you got the correct answers. I think what's wild about these is that some of these just are dependent on one substance, the gas. And so, you got this big equation here, but it only depends on the carbon dioxide gas. Or this last one only depends, or the third one here only depends on the hydrogen, not the water, not the iron 3 oxide, just the hydrogen gas. All right, and then here both of these are aqueous, that's why they're both included here, but the pure mercury is not. And then the last one looks like this. So I hope you got those right. It's easy. You should do very well on a quiz or an exam. These shouldn't take any time. These should be bam, 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 got the answer, let's move on to something more complex. So you shouldn't dwell a lot of time on this. The main thing is to search your balanced chemical equation and what are your pure solids and pure liquids, and know that those will be integrated into the equilibrium constant. Simple problem. All right, so this is where I find students, I don't feel like they spend enough time on this section, and these are these tools I've been talking about. These are really important, and you have to know these tools when you're doing chapters 16 and 17. So the first tool here is we have a balanced chemical equation, 2 moles of nitrogen oxide, and that's going to react with oxygen to form 2 moles of nitrogen dioxide. Notice this is homogeneous equilibrium. They're all gases, so it's a homogeneous equilibrium. And when we write the expression, this should be old hat now. We have the product raised to the coefficient divided by the reactants raised to their respective coefficients. But what would happen if I multiplied this entire equation by 2? Okay, multiply the entire equation by 2, I get this reaction. 4 moles of nitrogen oxide, 2 moles of diatomic oxygen yields, or just oxygen, yields 4 moles of nitrogen dioxide. So here is what this expression would look like. So the difference between this expression and this expression is not just the number 2, it's the power of 2. So I take this equilibrium expression, which is K at subscript C, concentration, and to make this expression become this expression, I have to square everything. Square it. Not multiply it by 2, but square it. So whatever the multiplier is here, that's what you're going to raise the power of the equilibrium constant or the equilibrium expression. So that's tool number 1. You double the reaction, you square the equilibrium constant. You triple the reaction, you cube the equilibrium constant. So it's not multiply, it's a power of. And you can see it. That's why I think this is an important slide, is if we clean this up and you look at it without all the markings, you can see that oops, I'm not going to be able to do that. You can see that it's a power thing. It's not a multiplication thing. All right. All right. The next tool is what happens when we combine equilibrium combine chemical reactions. So here we have the reaction we just had, and then we're going to combine that with hydrogen reacts with oxygen to form water. So we're going to combine the two equations. When we combine the two equations, all my reactants are here, all my products are here. The reaction's reversible, which says equilibrium can be achieved. And then we write the expression. Well, that's easy. We just take the nitrogen oxide here, the oxygen here. This is also a homogeneous equilibrium, so that's why it's easy to go directly from the equation. We don't have to evaluate, oh, is this a solid or a pure liquid? And so we plug these in, and then don't forget the coefficients. Coefficient, coefficient, there's the power there. Same thing here. Coefficient, coefficient. We see the power here and the power here. So what do you think the equilibrium, I've marked it through here, but what do you think the equilibrium expression for this is going to be? All right, well, let's look at it. Since you combine the two equations, that should look like we multiplied the equilibrium expressions together, right? So we actually multiply them. We actually multiply. So this one has the first one has a certain equilibrium constant. Second one has a equilibrium constant. I multiply those together, and I will get the overall equilibrium constant for that combined reaction. And I'm sorry they didn't really show a slide for that. They go into this general form. I think that's a little bit of a mistake. But I do want to say this is one of the most important slides in the whole chapter right here, because this shows you every tool possible. If I reverse the reaction, then the equilibrium constant is 1 over that constant. If I reverse it, all right, the reciprocal. So looking at this reaction here, if I reverse the reaction to this, then the equilibrium constant for this reversed reaction is the reciprocal of this equilibrium constant. All right. If I double reaction A, then I raised to the power to 2. If I double it, I raise it to 2. If I triple it, I raise it to 3. Here's the one that gets a lot of people. If you multiply it by half, that's the multiplier. Then these become 1/2. And it is the square root. This something raised to the 1/2 power is the square root. I think most students get it when you write it as a 1/2 because they just see it as a multiplier, just like this is the multiplier up here. That makes these numbers here, these coefficients or powers here. But the 1/2, for some reason, students kind of trip up on if they see it this way, especially. But just remember, something raised to the 1/2 power is a square root. The last one, we combine the two reactions together. This is an intermediate, so that's why we don't see that in our final expression. So it is the products D and E over the reactants A and B. And again, to get the equilibrium constant for this new reaction, we have to multiply the equilibrium constant of the first reaction times the equilibrium constant of the second reaction. So spend some time. Maybe you want to make some flashcards on this, but you need to know these 3 tools, not just this chapter, but also chapter 16 and 17. Very important slide. All right, so if you understand that, you should be able to answer all of these questions here. So it says the following reactions have indicated equilibrium constants at 100 degrees Celsius. And the question is, determine the equilibrium constant at concentration for the following reactions. So first thing you do is you look at this one. This is what we're going to compare it to. This is our original equation. We have the equilibrium constant for that. So what do you notice about this reaction? How does this compare to this reaction here? And you'd say, oh, it's just the reverse of it. So if it's the reverse of it, I would say the equilibrium expression or constant would be 1 over 0.014. And that would give me the equilibrium constant for the reverse reaction. All right, what about the second one? Well, you can look at that and you go, well, it's not reversed. It's the same reaction. It's just that this one's been doubled. So here's why I find students have a little bit of trouble with. So what you need to do is you need to, what number do all these numbers go into? 4, 4, and 2. And you would realize that the multiplier is 2. It's really important that you identify the multiplier, because the multiplier is what you're going to do over here. You're going to go 0.014, and the multiplier becomes the power to find out this new Kc doubled. All right, equilibrium constant doubled. All right, what about this one? This is the one that a lot of students find is really tricky, and they've got a typo here. That's why that box is there. It should be a plus. So you know it's not flipped, but you know the coefficient has gone from 2 to 1 for this. All right, so that means you multiplied by what? Well, that means the multiplier was 1/2. And so this is going to be 0.014 raised to the 1/2 power, and it could be written as the square root of 0.014. So those mean the same thing, and that's going to give you the equilibrium constant for this reaction. The next reaction, you're going, wow, what's going on here? Well, you see chlorine's introduced, and there's no chlorine in this first reaction. So we got to look at the next reaction. Oh, there's chlorine, and it's on the reactant side. It's on the right side. We need both the chlorines on the reactant side here, and then down here in my final equation. So what happens if I combine these two reactions together? Well, that bromine and that bromine cancel out because they're intermediates. I'm going to have nitrosyl bromide and chlorine on the reactant side, 2 moles of nitrosyl bromide and chlorine on the reactant side. And on the product side, I'm going to have 2 moles of nitric oxide and 2 moles of bromochloride. And that's what I have here. So that tells me I added reactions 1 and 2 together to get this reaction here. And so if I add those together, I'm going to multiply Kc for the first reaction times Kc for the second reaction. and that will give me the value for that one. And then the last one, well, the last one, you can see that it's flipped, and we are still combining the reactions because, and the yield sign didn't show up there. And so maybe for this one, let's see. You know it's flipped, and you know it's 1/2 is what you know. And the reason why you know it's 1/2 is this D and E look the same. It's the same substances here, but you can tell it's flipped. And then you can, if you want to see what the multiplier is, you look at this chlorine. It's 1 here, and it's 1/2 here. So this reaction is flipped. So let's say we solve for this one. We call it K3 here. K3 for D here. All right. To make this easier, so it's going to be 1 over K3 squared. To the 1/2 power, 1 over K3 to the 1/2 power. Because the multiplier here is 1/2. We can tell by this that it's 1/2 compared to that. So it's 1 over, and it's flipped, so that's why it's the reciprocal. So it's 1 over K3 to the 1/2 power. Or you could write it this way. 1 over the square root of K3. All right. So I hope that you'll take the time to do this one. If there's something you don't understand about these last 2 slides, email me, because I can't stress enough these tools are that important. You're going to be using them throughout, and I just hate seeing students get dinged for this in chapter 16 and 17 because they didn't learn it in chapter 15. All right. So sometimes we do reactions that only contain gases. And gases not easily, sometimes it's much more easily to measure the pressure of gases than the concentration of gases. So here we have a homogeneous equilibrium. So that's the first thing you need to, these are the things that should run through your mind. I have a balanced chemical equation. I have a homogeneous equilibrium. I'm going to write the equilibrium expression in relation to concentration. That's what we're going to do first because that's what we've seen. So it is products over reactants. Coefficient here is 2. This is raised to the 2nd power. And the brackets mean concentration. So make sure you remember that. Brackets mean moles per liter. But for gases, it's a lot more convenient if we're doing gases in a container, and we don't, you have to know the volume of the container. It's just better to have a pressure gauge here and see what the pressure of the gas is. So we want to know how do we write equilibrium expressions in relation to pressure. So Kp means not at concentration but at pressure. Notice we don't use brackets now, we use parentheses. And we would have the pressure of the nitrogen dioxide gas raised to the 2nd power divided by the pressure of the dinitrogen tetroxide. And you say, do they have the same values? There's a little difference here. So that's what we want to talk about, is what is the difference between Kc, equilibrium constant at concentration in moles per liter, versus Kp at pressure. So you guys know this. You know that from Chem 170, Gen Chem 1, that PV equals nRT. And the relationship here is that if I take P and I say that's equal to N over V RT, you go, oh yeah, that looks like concentration, doesn't it? Moles per volume, so moles per liter. So there's the relationship, is that pressure is related to concentration times RT. So that's what they're showing here. Here's the expression with relation to concentration. Here's the expression related to pressure. But we got to think about PV equals nRT. And so we have the pressure of A is equal, just follow this. This is what we just did. So this is concentration. So they transform that into that. And then you have RT. So the pressure with respect to A is equal to the concentration of A times RT. And the pressure with respect to B, the product, is equal to B times the concentration of B times RT. So when we look at the next slide and we plug in the pressures, we get, whoops. So we plug in what we just solved for, the pressure with respect to B and the pressure with respect to A. And because we're doing B over A, notice it's RT B minus A. All right, let's think about this. What we're doing here, we're plugging in what we just saw for the pressure B. We're plugging in what we just saw. Actually, I should do it that way, right? And we plug in what we have for A. And both of those had that multiplier of RT. But here's what we have to do. Because it's B divided by A, we subtract. And these are exponents. Remember, you subtract exponents when you divide. So that's why it's B minus A. So B minus A is equal to delta N, which is the number of moles of gaseous product minus the moles of gaseous reactant. And here's what you need to know. If the change in number of moles of gas is equal to 0, then RT raised to the 0 power is 1, and Kp and Kc will be exactly the same. So if there's no change in the number of moles from reactants to products or products to reactants, then delta N becomes 0 and Kp and Kc are exactly the same value. But if there is a change in the number of moles of gas in the reaction, then delta N is not going to be 0. And if it's not 0, then this RT has a factor to play in relating equilibrium constant at concentration versus equilibrium constant at pressure. Really important to know this. You're going to be tested on. It's going to be on the quiz. It's going to be on the test. It's that important. So make sure this is another tool. So we talked about the 3 other tools on the other slide. This is the 4th tool right here. All right, so let's look at an example here. And again, these are not hard problems. They're fairly quick. I mean, all you do is you come up here and you go, okay, I've got a mole of gas here and a mole of gas here, and I end up with 2 moles of gas here. You go, okay, well, that's 2 minus 2. Delta N for this is equal to 0. So in this case, the R is this, the T is this, but you're raising it to the 0 power, so Kp equals Kc. That's how quick it is. And so if you know either Kp or Kc, you've got the answer. It's that quick, but you got to be able to, quickly analyze this up here and go, this is a balanced chemical equation. It's all homogeneous. It's all gases. I'm trying to relate Kp to Kc. So here's your practice. So right off the bat, when I'm looking at a problem like this, I go 1 mole of gas. So it's balanced. Let's go through the sequence again. It's balanced. It's all homogeneous. It's all gases. I've got phosphorus trichloride reacting with chlorine gas, forms phosphorus pentachloride. The delta N for this is going to be 2 minus 1. So I'm going to have 1 for my delta N. So that means the RT is going to play a factor here. For number 2, balanced chemical equation. So 2 of them are gases. We have a liquid over here. Oh, that's a little trickier. So this one you have delta N equals 3 minus 0. The difference is 3. So 1 mole of gas here, 2 moles of gas here is 3. 3 minus 0 is 3. Oops, I did that wrong. Yeah, I did. Let's redo that one. I don't know what I was thinking. Did I do that one wrong up there too? Absolutely. All right. Got a little too fast. Let's go back. This first one up here is delta N equals 1 minus 2. It's always products minus reactants. So this is negative 1. This next one here is delta N equals 0, because this is a pure liquid, minus 3. So my answer is negative 3. All right. And then the last one, it's 3 moles of gas, 2 moles of gas. So delta N is equal to 2 minus 3, which is a negative 1. That's interesting. All right. So you see what I did? I got a little too fast. And it's always products minus reactants. Okay, so the first thing they do is they write the equilibrium expressions in relation to Kp. And I would do that too. Okay, so you write those. And we actually didn't have to compare the two at this point. They're not asking us. So we did that part. Okay. So let's go on. That was just actually write the KPs. I actually took a little. That's what was throwing me. As I was thinking, this is a little harder problem than what I would have started out with. So here's where you get the chance to look at KP and KC. All right, you got dinitrogen tetroxide. Again, when you're doing these problems, get your naming down. Work on it. Nitrogen dioxide. It's balanced. It's homogeneous. It's gases. They want to know what the KC is. All right, you go up here, you go delta N is equal to 2 minus 1, so we get 1 for our change in number of moles of gas. And then here's the thing you got to memorize. Kp equals Kc times R times T raised to the power. In this case, it's going to be the 1 power. That's why they don't show it. And then all you do is they tell you the temperature. Most common mistake is you don't convert it to Kelvin. It has to be converted to Kelvin. How do you know it has to be converted to Kelvin? Because when you write out the R, you should write out the units, and you would see this Kelvin here cancels out with that Kelvin there. And again, the units are meaningless, but that at least gives you a hint that this temperature has to be in Kelvin for this to work. So there's Kc. There is R times T in Kelvin raised to the first power, and that is what Kp equals. So Kp equals Kc times RT. Easy problem. These are not that difficult, but these are the tools you're going to need in order to be successful in the next chapters. But you're going to get tested strictly on this, so don't think like, well, it's not that important. Yeah, it is. You're going to get graded on it here in chapter 15, and it's an underlying grade in chapter 16 and 17. All right, it's 32 minutes into this. I am going to go on and do this section as well. So it says predicting the direction of the reaction and calculating the equilibrium concentrations. Predicting the direction of the reaction. Okay, this is super important. This is something you want to focus on. So we talked about reaction quotient in the first video for this chapter. And so we talked about reaction quotient, which is Q. Q is non-equilibrium concentrations. You only have equilibrium concentrations when you use K. So K is equilibrium, Q is reaction quotient, is non-equilibrium concentrations. And here's what you got to remember. If Q is less than K, let's do something real simple here. We got A going to B. And let's say that both of these are gases. Let me just make it easy. All right, so our expression is Kc is equal to the concentration of B over the concentration of A. So Q looks just like it. It's just that we're not dealing with equilibrium concentrations. We are dealing with non-equilibrium concentrations. So in order for Q to be equal to Kc, they got to have the same ratio. They got to have the same. Now that doesn't mean they have to be the same numbers, but when I divide B by A, in both of these cases, they have to have the same number. So let's say Q is less than K. That means the ratio of the reactant over the product is less than K, which means that you don't have enough B present, or you got too much A present. That's two different ways to think of it. But either way, when Q is less than K, that means B is going to have to increase and A is going to have to decrease to get where Q is equal to K. So in this case, you know that the system, the reaction, is going to proceed in a forward direction from left to right. So here's what you're going to hear over and over when we're talking about this. You're going to say the reaction proceeds forward in the forward direction. I hear it said that way. I also hear it said the reaction is going to proceed left to right. Or I hear it, we're going to go from reactants to products. So there's three different ways to say this reaction is going to go towards the products. Left to right, forward, or from reactants to products. Now, if it just so happens that Q equals Kc right off the bat, that means you have chosen concentrations, initial concentrations, that are equal to equilibrium concentrations. And the ratio comes out to be exactly the same for both. That doesn't happen very often. It's kind of rare. I feel like it's almost contrived. But if the reaction quotient equals the equilibrium constant, then there's no net reaction in either direction. The reactions, it's already at equilibrium concentration, so you're not going to see any change there. All right, so what's the third one? Well, the third one has to be when Q is greater than K. And this is the one that throws students the most. But if they understand what we've just talked about, if Q is greater than K, that means that B over A is greater than it should be. It's greater than what the equilibrium amounts. And so sometimes to show initial, we'll do that. Oops, I did that wrong. Over A. So these are initial. There's non-equilibrium concentration. So if this is greater, what does that mean? Well, B is going to have to decrease, and A is going to have to increase to bring Q down equal to K. So if Q is greater than K, the reaction is going to go in reverse. The reaction is going to go right to left is what we say, or in reverse, or from products to reactants. Make sure you know this. This is really important because most of the time you're going to be given non-equilibrium concentrations, and then you're going to have to determine which way the reaction is going to proceed in order to solve the problem correctly. So again, it's either Q is less than K, Q is equal to K, which is pretty rare, and then Q greater than K. If Q is less than K, you know the reaction is going in the forward direction. If it's equal to K, there's no net reaction. And if Q is greater than K, some of the product's going to have to be converted back to reactant to raise the value of to lower the value of Q to get it equal to K. All right, so let's look at a problem. So at 375 degrees Celsius, the equilibrium constant for the reaction is nitrogen gas reacts with the hydrogen gas to form ammonia. We have a balanced chemical equation. It's all gases. Equilibrium can be achieved because we see the double arrows here. So it's homogeneous. These are the things you want to look at. Then you look at this. The equilibrium constant is 1.2. Tells us that maybe the products are favored just a little over the reactants. And remember what we said, if K is really large, much larger than 1, the reaction proceeds in the forward direction, or the equilibrium lies in the forward direction. That's what I want to say. The equilibrium lies. Let's do it this way. The equilibrium lies with the products. Let's do it that way. That's a better way to think of it. If K is less than 1, then the reactants is what we mostly have at the when we have the reaction comes to equilibrium. Really, these numbers are usually greater. If it's greater than 100 or less than 100, maybe that's what I should say. When K is 1.2, it just tells me this is favored a little bit, but there's all three things going to be present at equilibrium. So the start of the reaction, so this is a key. Read that first. I think this is what throws students off. When they say start of the reaction, these are the concentrations. These are non-equilibrium concentrations. So read carefully. If it says the start or initial, you know we're not dealing with equilibrium concentrations. It says determine whether this system is at equilibrium. That's where we're going to determine whether Q equals K. That's what the speak is there. And if not, determine which direction it must proceed to reach equilibrium. All right. So we know what we're really going to be solving for initially is the reaction quotient. It's going to be the product concentration raised to the second power divided by the reactant concentration raised to the third power for the hydrogen because of the coefficient there. And then we're going to plug in these values, and we're going to find out what's the relationship between Q and K. Okay, reaction quotient Q, equilibrium constant K. All right, so that's what we have. Notice, so what they did, they put the word initial. You can put a not symbol or an I don't care, it doesn't matter. But you do want to have a way to signify to you these are non-equilibrium concentrations. So we plug in those starting concentrations raised to the respective powers. We get this for a number. If you should do this on your calculator, make sure you get this number. If you're not getting that number, then you're probably having some problem with the exponential key. All right. So 0.61 is what we get for the reaction quotient, which is less than 1.2, which is the equilibrium constant. So if Q is less than K, which way does the reaction go? And you should say it goes to the right. So here they don't say left or right, they just say it goes to the right to establish equilibrium. So that's another way to say it. Instead of saying the reaction goes from left to right, you just say it goes to the right. It increases the products, it decreases the reactants. That ratio, I want you to think of it in terms of a ratio. This ratio is less than 1.2. How do we change these concentrations so the ratio gets up to 1.2? That means the product has to increase and the reactants have to decrease to do that. All right, calculating equilibrium concentrations. This is really important. This is what you're going to be doing in the next chapters. You're going to try to figure out what the equilibrium concentration is for the hydrogen ion or hydronium ion or the hydroxide ion to determine the pH, because pH is measured at equilibrium. So here we have cis still being. What does cis still mean? What does it mean? It means these two benzene rings are on the same side of the double bond, whereas this is trans, where the benzene rings are across from each other. So that's called trans stilbene. This is cis stilbene. The equilibrium constant concentration is 24, so this is slightly favored over the reactants. Not much, though. So both things are going to be present at equilibrium, close to the same concentrations. So that's what we can interpret from this. All right, so we're going to set up a table. And if you've had this before in high school, you probably called it an ICE table. So here it is, initial, change, equilibrium, and they call them ICE tables. So in an ICE table, with only one reactant and one product, you're going to have two columns. You're going to have the initial concentration of the reactant. There was 0 concentration of the product to begin with. And so right off the bat, you know that Q is less than K. Because if you don't have any product initially available, then it's 0 over 0.850, the original concentration of the reactant, which equals 0. And if Q equals 0, that's always going to be less than K. So you know this reaction is going in a forward direction, and you don't even have to calculate that. But I just wanted to emphasize that because I think students have a hard time deciding which way the reaction goes. This one's automatic. If you don't have any product, it's going forward. And if you didn't have any reactant and you only had concentration of product, which seems strange, but remember the reactants and products are decided by the equilibrium expression, then the reaction go in reverse. But in this case, since we don't have any product, we know the reaction's going in a forward direction. How much of this stuff are we going to lose? Well, because it was cis stilbene, I'll just call it CS, going to trans stilbene, and the molar coefficients were 1, or the coefficients in front were 1, then we know we're going to lose X amount of this, and we're going to gain X amount of the trans-stilbene. So that's why in the change right here, the change is we're going to lose X amount of the reactant, we're going to gain X amount of the product. And so if we add the initial and the change together, we get equilibrium. So here's what it is at equilibrium. We had an original concentration of the cis-stilbene. We're going to lose X amount of it. We had 0 of the product, and now we're going to gain X amount of it. Yeah, we lose X amount. I said gain, I think. We lose X amount of the cis-stilbene. We're going to gain X amount of the trans-stilbene. You got to write the equilibrium expression. We know how to do that at this point. It ought to be very easy. That's very quick. So then we plug in our equilibrium amounts for the product and the reactants, raised to the respective powers, which is 1. So that's why we don't have any numbers here or here. So we get this. We plug in the values. We know what the equilibrium constant is. That's given in the problem. We know the initial concentration of the cis-stilbene. What we don't know is what X is. So we got to solve for X. Well, that's easy to do. You're going to have 24.0 times 0.850 minus X equals X. We just multiply both sides by what's in the denominator to get X by itself. So then 24.85, I don't know what that number is. You can figure that out. That's going to be some number minus 24.0x, because you got to multiply this by this and this. And that's going to equal X on this side. And then you got to move the other over. So then you're going to have some number equals 25x. Because remember, here's a common mistake right here. You got 24x here. You're going to add 24x to both sides. All right. Remember, there's a 1 in front of that x there. That makes this 25x. So don't forget that. If there's just an x here, the coefficient in front is 1. So 24 plus 1 gives me 25x. And then you're going to solve for x. You're going to have this number divided by 25. And x is going to come out to be that number there. Now, you're not done at this point. You got to read the question. If they want to know what the concentration at equilibrium of the trans-stilbene is, you come back up here, you plug it in here. Sometimes this gets complex. It's real easy here, but sometimes it's more complex, so you've got to really make sure you do an ICE table and see what they're asking for. To find out the equilibrium concentration of the cis-stilbene, you're going to take that number, plug it in here, and subtract that from 0.850. And that will give you the concentration of the cis-stilbene. So these are long problems, requires a lot of organization, slow movement through it, not something super quick. I mean, yeah, sure, there's steps that are quick like this, but you got to be methodical about it. All right, so they do this for us. They subtracted the 0.816 from 0.85. We get this left over of the cis-stilbene. We gain this amount of the trans-stilbene. That makes sense because the equilibrium constant was 24. It favored the products over the reactants, and we see that here. But both are still present. And you can check your work. You can divide the product by the reactant, and you should get this number here, which is the equilibrium constant. So that's a good check. If you're not confident about your answer, you want to make sure you did it correctly. It's worth double checking. All right, let's have you try one. So again, I'll pop it up here. I want you to stop the video, try to work this out on your own, and then let's see where you are. All right, so let's look at the prop. First thing you got to have, balanced chemical equation. Yes, we have that. We know the phases of matter. We know that equilibrium can be achieved. Next thing I automatically do, we know it's homogeneous. The first thing I do when I do an equilibrium problem is write Kc. I'm going to say it's the hydrogen iodide raised to the second power divided by the hydrogen concentration and the iodine concentration, both raised to the first power. They tell us Kc for this is 54.3, so I'm going to make a note of that. At 430 degrees Celsius, what will the concentrations be at equilibrium if we start, again, there's the key, start with a concentration of both hydrogen and iodide at 0.240. So if I was organizing this is what I would do. I would say H2 naught is 0.240. I would say I2 naught is 0.240 molar. And then I would have HI equals 0 molar. Okay? So what does that tell me? Well, that tells me that Q, I always do a Q, even though it's simple like this. I say Q is less than K, because Q is going to be equal to 0, since we don't, if you plug it up into this expression, this would be 0, and these would be 0.24, and that, so Q would be 0. Q is going to be less than 54.3, so I know the reaction's going in the forward direction. So I think it's important to go through that step, because you're going to have ones that don't go in the forward direction. If you just get in this habit of, here's how I'm evaluating it, you won't make mistakes. All right, so we know the reaction is going to go in the forward direction. So the next thing we need to do is we need to write our ice table. You're going to be doing lots of ice tables. You might as well get used to it. Again, next chapter and the chapter thereafter, you're going to be writing ice tables. So what do they look like? Well, you have hydrogen in one column, iodine in the other column, and the hydrogen iodide, wished it would have been over here a little more, but there it is. You know this reaction's going in the forward direction. If there's none of the product available, you know the reaction's going in the forward direction. Q is less than K. So then, how much of this am I going to lose? Well, I'm going to lose X amount of this. How do I know it's X? Because the coefficient here is 1. I'm going to lose X amount of this because I know the coefficient is 1. And I'm going to gain 2X amount of this because the coefficient here is 2. That's why it's important that you have a balanced chemical equation. So at equilibrium, this is going to be 2.240 minus X. This is going to be 0.240 minus X. This is going to be 2X. All right. Makes sense. All right. I'm going to fill it out for us. All right. Here's the expression. We've done that already. Here's my ice table filled out. We've done that already. Now, plug in these values or terms into this expression, and this is what we get. All right, so this is where students have problems mathematically, right here. Okay, so let's focus on this. You got 2x squared in the numerator, and 0.240 minus x times 0.240 minus x is the same thing as 0.240 minus x squared. So you go, how am I supposed to get rid of this squared term? So you're going to take the square root. You can do it both ways. You could say you're going to raise everything in this ratio by 1/2, which means you're going to raise this by 1/2. And then this shows that that is the square root of 54.3. The 1/2 times 2 here, that makes that 1. And the 1/2 times 2 makes that 1. And so now we get this expression. So make sure you can do this. This is where I find students start to fall apart on these problems. So you got to take the square root of 54.3, and they didn't show that, so let me go on and do that for you because I think you need to know. So let's see. That equals 7.369. So I carry more digits. 7.369. All right, so then the next thing you're going to do is multiply both sides by this 0.240 minus x. You got to do it to this side. You got to do it to this side. Everything in the parentheses has to be multiplied by that number. And then you solve for x, and you should get this number here. So it isn't the chemistry, it is the math. I think that's what hurts students here. It's not that hard. I don't think anything we've covered so hard seems outstandingly hard, but it is the math in this region that I find students have difficulty with. But you're going to get good at it. By the time we get through 17, this is like easy. So if you are struggling with this, you just need to do more problems. Maybe do some of the odd problems in the back of the chapter, but you got to get this process down of how to mathematically manipulate this equation to solve for x. That's what we're doing. Okay. So even when you get a number over here and you get your x's over, you still got to divide by whatever number of x's you have. And in fact, just a precursor, I don't know what this number is. It's this number times that, but this is going to be this number times x, and then you're going to bring it over to the other side. It's going to be 2x plus, it's going to be this on this side. It's going to be 2x plus 7.369x. That'll be your total amount of x on this side, and you'll have some number over on this side, and you'll solve for it. Just try it out. If you need help, just let me know. Email me, set up an appointment, but I want you to try to work through the math for you to understand it. Now, here's another thing I see students do. They say, that's my answer right there. That is not your answer. That is not the answer. They're going to ask you what they're looking for in the problem, and I see students choose this as their final answer. No, your answer, you have to go back up here to your ICE table and plug in the x here for each one of these, and notice this is 2x, this is an x. So there's no answer that's going to come out to be 0.189. If they want to know what the equilibrium concentrations are, it's for hydrogens 0.240 minus 0.189. Same thing for iodine. And then for the hydrogen iodide, it's going to be 2 times 0.1849. And so you get for that what we see here. All right. So let's look at look at the next step. So it says, for the same reaction and temperature as in sample 15.8, calculate the equilibrium concentrations of all three species starting with these concentrations. So notice now, what's different about this one is we don't have 0 of the product. We don't have 0 of the product. We start off initially, say, there's the key, starting, and we have product initially present. So when there's product initially present, you definitely have to calculate Q, the reaction quotient. So it looks just like the equilibrium expression, but you're going to plug in these initial concentrations, and this is what you get for the value. And what you find out here is Q is greater than K, because K is only 54.3. So Q greater than K, which way is this reaction going to go? If I have hydrogen, and I'm not going to put the phases because I don't have enough space here, but hydrogen plus iodine forms 2 moles of hydrogen iodide. Which way is this reaction going to go? Well, it's because Q is greater than K, the reaction proceeds to the left. It goes back towards the reactants. And that's the problem. If you don't calculate Q, you get the wrong answer here. And I've seen students do that. Spend all this time doing it the forward direction, and that will be one of the multiple choice answers. That tells me what you did incorrectly. And then, you wasted a lot of time for that, and you lost points. So notice what happens here. It's an ICE table. Here are the initial concentrations that were given. You calculated Q. You said Q is greater than K. The reaction is going to proceed to the left. So notice here it's minus 2x. It's gaining X amount for both the reactants. You add those together, you get the equilibrium. Again, ICE table. You plug these values into the expression, you get this. And this is the kiss of death right here, because it's not easy to solve for this, right? It's not just take the square root of both sides, because these two terms are not the same. So anybody know how you solve a quadratic? How you solve a quadratic problem? You're going to have to know this. So, you have this in algebra. Solve the quadratic equation. Solve the quadratic equation. And you're thinking in algebra class, when will I ever use solving the quadratic equation? I don't know. Never. And you've been taught the FOIL method first, outside, inside, last. So the FOIL method, maybe that's what it's still called. I hope it is. But that's what you're going to have to use here. And I find a lot of students struggle with this. If you are struggling with this, we know that you struggle with this. In the appendix in the book, it talks about the quadratic equation and how to solve for it. So you're going to have to get some practice. Once you get the practice, this becomes old hat too, but it's going to take some practice here. Okay, so when you multiply the two terms that we saw in the denominator together, you should get this expression. And I don't like writing it this way. I would say x squared plus 1.04 exponential negative 2x, and then I'd have this on the end. But that's not the way they did it. So once they multiplied what was in the denominator, they multiplied both sides of the equation by that, and that's what we have here. We have what's on the numerator, what's on the numerator of the other side. There's the equilibrium constant, right? And then you got to get all your terms together. So then when you add this all together, you should get this as your quadratic equation. And notice the form. It's ax bx plus c, and you set that equal to 0. So I want you to practice going from the last step and getting to this step and then getting to this step, all right? And keep practicing that until you understand it. So again, let's see if I can write that. I can't write it, but that's what you do. You go from the last slide to this slide to get this. Now, once you get this, this is going to be your A term. This is going to be your B term, and your C term is this whole thing here. All right? It's the whole thing that we see right there, the negative 4.00 times 10 to the negative 4. This is called the quadratic equation. This is what you're going to plug it into. This is what it should look like when you plug it into that. What you're going to do is you're going to solve for this part here. You're first going to add it to this and then divide by this. And you should get an x that looks like this. And then you're going to take this term and subtract it from the square root of all of this. And you should get this term. And again, this is not chemistry, it's math. That's why you have to have college algebra before you take Gen Chem 1. But you should get these two roots here. That's what they're called, roots. And we would have had roots in this previous problem where we just squared both terms, but there's no such thing as a negative concentration. So we know that root is not acceptable. So this is the one we need to know to solve the problem. So that's what happens. You have two roots to a quadratic equation. One of them is either negative or it's a concentration that's larger than what you began, the initial concentration. So both of those types of roots are unacceptable and you throw those out. So on this one, because it's negative, we throw that one out. And this is this is what we're solving for, is this x. Lot of material, a lot of math on this slide, and if you're not getting this, if you can't manipulate the quadratic, what I would tell you to do is you're going to meet with a math tutor and do some of these problems and let the math tutor explain to you how you get the coefficients A, B, and C from the quadratic equation using this and solving for it like so and finding out what the proper root is. Once you get that, once you solve for x, then it's just like any other problem that we've done. You plug in the x value into the equilibrium part of the ice table, and you will come up with the equilibrium concentrations of the reactants in the product. So that part's not hard. It's that whole thing with the quadratic equation. And you're going to get practice on this on the assignment. I hope on the quiz you don't have one of these, although if they give you one of these, it's probably a simple one. So just keep that in mind. All right, next slide is when the magnitude of K is very small, the solution to an equilibrium problem can be simplified. So this is called the approximation method. And this is, everybody loves this slide because when K is really small, that's what they're saying, it's unnecessary to do the quadratic equation. All right, so that's what you're hoping for. You're hoping for it's going to be x squared over 0.24 plus x squared, and you can just, and then that equals K, and you just have to take the square root of both sides. Or the other thing you're hoping for is this K is really, really small, much, much smaller than 0. So in either one of these cases, the problems are fairly solvable fairly quickly. It's only when that K is larger and you're not getting equal values here in the denominator, then you're going to have to use the quadratic. There's not a lot like that, but I think it's important that you do it, especially you engineers. You've got to determine there's different ways to approximate real complex problems. Quadratic equation is one of them. All right, so let's see an example that makes everybody happy, and that is when K is really small. All right, so here we have diatomic iodine becoming monoatomic iodine. Here's our equation. We see it's balanced, it's homogeneous. It's easy to write the equilibrium expression. They tell us Kc for this is 3.39 times 10 to the negative 13. So right off the bat, here's the flag. Kc is super small. All right. It says determine the concentration of the atomic iodine, when in a 1 liter vessel, when with a charged initial concentration of 0.00155 moles of molecular iodine. So atomic iodine, molecular iodine. We don't have any of this initially, so we know what the ice table is going to look like. We know which way this reaction is going to go. It's definitely going in the forward direction because Q is less than K, because Q is equal to 0. So again, always do that. Always say Q, evaluate it. Just do it automatically. If this is 0, it's understood. It's definitely going to be less than K, and it's going in the forward direction. Why do I need to know that? Because that's what's going to tell me this is minus x, and this one is 2x because plus 2x because of the coefficient here. So don't forget that. That's why you got to have a balanced chemical equation. Here's my equilibrium concentrations of both the reactant and the product. I plug those into the expression. They've already done that for us here. Here is the equilibrium constant. And this is what I have over here. And again, if K was large or greater than 1, then you'd be going, I have to do the quadratic. But because this is what I generally, let me tell you what my gauge is here just to help you out. So this is 1.55 times 10 to the negative 3. This is 10 to the negative 12. Generally, when the difference between these is about 10 to the negative 4th, then I know the approximation, that I can approximate this x is negligible. All right. So if I approximate that this x is negligible, I don't have a quadratic anymore. All I have to do now is multiply both sides of the equation by this 0.00155. I squared the top term. Don't forget to do that. So 2x squared is 4x squared. And I see students miss this. It's a mathematical thing. What is that? Let's do one right here to see how bad this is. I've got 2x and I've got it raised to the 3rd power. Tell me what the value for that is. And if you get it right, then you should be pretty confident in your math. If you get this wrong, though, you're going to have to brush up on your math. So what is the value of 2x cubed? All right. Well, 2x cubed is 2 times 2 times 2. It's 8. And it's x cubed. If you said 6x cubed, that's not right. Remember, cube means 2 times 2 times 2, and then x cubed. So if you got that right, you're in good shape. If not, you're going to need to brush up on your math. But it makes it so much easier because this x is we assume it's negligible compared to this, because what this is saying is this. This reaction's not, even though it's going to go to the right, it's not going to go far to the right because it has such a small equilibrium constant. That tells you that the reactant is favored over the product. So very little change is going to occur on this side of the reaction. Now it's important change because we had 0. We're going to end up with something here. But we can approximate that the change in this concentration here is negligible compared to the original concentration. So this x is negligible because we have some of this already present. This is significant over here because you went from 0 to 2x. All right, so let's look at the next slide. Oops, went too far. All right, so we solve for this. We plug it in. Makes it much easier. No quadratic. Multiply both sides of 0.0015, divide by 4, and then take the, in this case it was the square root of both sides, right? Take the square root of what all this is, which is that number, and we take and then we have square root of x squared is x, and we get x equals that. All right, so then the question asks how much atomic iodine is present in equilibrium. So I take that value, put it in that 2x that's in our ice table, and we get that for our equilibrium value. They didn't ask us for the concentrations of the diatomic iodine or the molecular iodine. So all this problem asked you to solve for was the monoatomic or atomic iodine. All right, much easier. It's called the approximation method, not the quadratic, which is a type of approximation in itself, but this is just the approximation method where the change in x is negligible compared to the original concentration of the substance because the equilibrium constant is so small. So in summary of this section, just to summarize it to make sure everybody's on board, you construct an equilibrium table called an ice table, including anything that has a 0. You always calculate Q, and that determines which way the reaction will proceed. Then define X as the amount of a particular species and use the stoichiometric coefficients in terms of X. And that's why I find students, if you gain 2x, then it's got to be, if you see a coefficient of 2, like that monoatomic iodine goes to, the molecular iodine goes to 2 moles of monoatomic iodine or atomic iodine, then there's a coefficient of 2 there, that's got to be 2x. So this step is, again, a lot of people, step number 3, they don't look at that carefully enough. Step 4, for each species in the equilibrium, add the change. Make sure you know which way it's going and do the correct changes. Add those two together. You get the equilibrium amounts, the terms for equilibrium, and then you solve for X. Once you solve for X, just make sure that you don't say that's your answer. I know it's a lot of work and it's multiple steps, but you don't say it's the answer. That's X, and then you got to plug it back into the ice table to find out what the equilibrium species are. And then the last step is to check your work. You can always check it. You can always check it to make sure it's coming out correctly. So you should be able to plug in those concentrations and get the same equilibrium constant. If you don't, then you've made a mistake. So if you have time, check your work. If it's a quiz or an exam and you've got time, you've gone through the whole test, and you've got some time, you can always check your work. All right. Last problem of this section. This one we're changing it up just a little bit. Same type of problem. We're just dealing with KP instead of KC. KP is the same. And the reason why it's the same, look, 1 mole, 1 mole, 2 moles here. The change in delta N is equal to 0. It says determine the equilibrium partial pressures. Now notice we're not dealing with concentration. They want to know what the pressures are of the reactants and products at equilibrium. And notice these don't have concentrations up here. It's 5.75 of both the hydrogen and iodine. And again, we don't have any hydrogen iodide to begin with. So we know this reaction Q is less than K. We know the reaction's going in a forward direction. So here we go. Set up your ice table. This should be old hat by now. Plug it into the expression, and you go, oh, this is nice. This is nice. This is all squared, same term, so you can take the square root of both sides. Takes the square out of here. You can then solve, once you get this number, you can multiply it by this, manipulate the equation to solve for x. We like these problems. It's much easier. Oops. Plug those into the expression, equilibrium constant. Or put it in your ice table. Let's say that correctly. Put it in your ice table. And here, I will say this. They finally do it correctly here. They show you every step that you need to know. You took the square root of both sides. You get this. You got to multiply both sides of the equation by this to get this x by itself. Then you multiply the equilibrium constant by what's in the parentheses, and you get this. Then you got to move this over to the other side. There's a typo there. There's a decimal there. And you get this equals that. Divide both sides by the 9.369, and you solve for x, and you get that. Plug this into the ice table, the equilibrium part. Find out what the equilibrium pressures are. So you can see there's not really much difference between solving for KP and KC, unless we're trying to compare the two. This was all in KP. It's all in atmospheres, no molarity concentration. So it solves just like, I think some students get a little confused like, oh, it's really going to be harder or different. It's not. KP and KC, when treated as individual things, they solve the same. It's just that one you're dealing with moles per liter, the other one you're dealing with pressures. All right. That's where we're going to stop at on this lecture. It actually got to be quite a long one, but you can watch it in parts. You don't have to watch it all at one time. This next section will be the last section, I believe, and it's over Le Chatelier's principle, and it has to do with homeostasis, where we are at equilibrium. We apply a stress to the system, and the equilibrium will shift in such a way as to relieve that stress. So you see this a lot in biology. You can see it in the engineering with the car thing that I've talked about previously. So this is a really important section. It shows us how when we add stresses to something that it's at equilibrium, how that stress is relieved. So we'll stop here, and we'll see you in the next video.